Our first chi-square video explained the theory of the nonparametric test, where we're dealing with nominal or ordinal level variables, and therefore we're looking at counts in the various categories rather than computing parameters and statistics like means and standard deviations. And we used a few examples there. In this example for carrying out the computations and actually finishing the test, I'm using data from the Titanic sinking in the early part of the 20th century. And we'll do a fairly simple goodness of fit test that is not particularly interesting or surprising in its results, and then we'll have a more interesting test of independence. So the first set of data that's sitting here on the window is showing us the number of male passengers, adult male passengers, and the number of adult female passengers to add up to a total of 1188 adult passengers. I've removed the children from the data set because their gender was not available, and I wanted to be able to count people as either male or female. So this is the observed number on the actual Titanic as it set sail. I'm going to compare it to the general population, where approximately half of the people were male and half of the people were female at the time. Now, it's not surprising that in the early part of the 20th century there were many more men on this ship than women. Women didn't travel very much at that time period, so we're not going to get a result that surprises us, but it does give us a way of learning to carry out the calculations. So I know what my sample shows. The second step for carrying out my chi-square computation is that I need to find out how many I would expect of men and of women if this 50-50 null hypothesis were true. My null hypothesis is equal numbers of men and women traveled on the Titanic. If that were true, the number of men would be equal to 1188, the total adult passengers, divided by 2, and the number of women would be equal to 1188, the total adult passengers, divided by 2. Now, because I only have 2 categories and my null hypothesis is that people are equally divided, these expected counts are the same. If I had more categories, and especially if I did not expect an equal division, perhaps I thought that 2/3 of the passengers would be male, I could test my hypothesis of 2/3 male against the number that I have here and find out if that was in fact a good hypothesis. But we're using 50-50. We're going to get some really strong results, but it will let us see how to carry out the computations. The chi-square equation computes what I'm calling a part for each cell. So in each cell, I have to compute the observed value minus the expected value and square that, and then I divide that squared difference by the expected value. And I could do this in several steps. I could do the computation of the difference and then square it, but I'm choosing to do it all in one function, and I'm going to use the power function as part of the equation. The power function uses the word power, and it means that I'm going to raise some number to a power. And when I square something, it means that I'm raising it to the power of 2. The thing I need to raise to a power of 2 is the observed value minus the expected value. So this function will use the word power, and then its argument, or the part that it needs to have to work on, is observed minus expected, a comma, and then the power, the particular power that I want, which is 2. And then once I've got that power, it's the numerator of my equation. The denominator is the expected value. So let's see what it looks like. I put an equal sign. I'm working on the numerator. I start looking for my power function, and you can see that the actual little description comes up, returns the result of a number raised to a power. Now, I'm not going to give it an actual single number. I'm going to give it this difference, observed minus expected. So I double click to get my power function going. and it says, okay, I've done power. The first thing I need to do is put in the number. Well, I'm going to do it by clicking first on the observed, and then a minus sign, and then the expected. So my number is observed minus expected. When I put in a comma, that lets the function know that I'm ready to go on to the second part. I need to tell it what power to raise this to. If I put in 3, I'd be cubing it, but I only want squared, so that's what I'm going to do. Once I've put in the power, I can close my parentheses. That part of the equation is done. It's the numerator, the difference between the observed and the expected, squared, and then I have to divide by the expected value. So when I hit enter, Excel will carry out all these computations for me, and I get this number 55. Now, because of the way Excel is set up, if I drag to the right, it's going to take the function here and fill in all the cells that are one to the right. So where my observed was in the males column, it will pick up the observed in the females column, the same for the expected, and it'll apply the same power to them. So I'm not going to have to type it all again. I just drag and let go, and it computes the results for me here. And you can see as I click in this cell, it put in all of the things in the equation just as I needed them, but it moved over to the D column to do it. So that kind of thing can be really convenient. If I had 5 or 6 categories, I'd only have to type the equation once, drag over, and it would do all of them for me. So these are the cells that I've computed as part of the chi-square, but my chi-square equation tells me to take these elements and add them together, and the actual chi-square statistic is their sum. So in that cell I'm going to do equal and the word sum and drag over the range that has the component parts in it, close the parentheses, and it gives you my actual chi-square value. I can tell you just looking at it, this is an incredibly large chi-square value. We have exactly 1 degree of freedom here. Our degrees of freedom for the goodness of fit test is the number of categories minus 1. So I had 2 categories, minus 1 gives me 1 degree of freedom. If you look at the table in the end of the textbook and find the critical value for a chi-square for 1 degree of freedom, you'll see that it is much, much smaller than this 111. But rather than look things up in the textbook, I'm doing this entire problem with Excel. I'm going to apply my 0.05 alpha level to say that if I get a p-value less than 0.05, that I would reject my null hypothesis, which was that the Titanic had equal numbers of men and women. And the number that we see here is actually going to be quite surprising. I need to use a function called chi-square distribution right tail. And I think this function may not be available in Excel 2007 and earlier. I'm still looking to see if there's a way of getting the earlier versions of Excel to calculate it. I know it is there in the Google Sheets, so if you have one of those early versions of Excel, you may need to do this same work up in Google Sheets. It is not, it doesn't function any differently, except it gives you the up-to-date equations. So I need this function, and then I have to put in the cell that has the statistic, this one that I've got here, and my degrees of freedom. So let's see how it works. I put in my equal sign. I've got a chi-square. As soon as I start to type chi-square, you can see it gives me a lot of them. The second one down is the one I need, chi-square.dist.rt for right tail. So I click on that, and it's highlighting for me that the first thing I need, it calls it X, the actual statistic number. So I'm going to click on that cell, put a comma, and then the degrees of freedom. And seeing as I have a cell with that, I'll just click on it, close my parentheses, And this number looks quite strange. It's got this E in the middle of it. It's scientific notation, and it's telling me that the p-value for a chi-square this large is 4.53 with 26 zeros in front of it. In other words, it's a really minute number. Compared to 0.05, it's like a pinprick. If I were trying to graph it on the chi-square distribution, my tail that had the alpha area filled in would have one teensy dot way at the far end that would be the area represented by this p-value. In other words, the likelihood of getting 776 men and only 412 women on the Titanic, if women traveled equally to men at that point in time, is this incredibly small number. So my decision will be to reject the null hypothesis, because I got a result that is just completely inconsistent with it entirely. Now, this isn't surprising. We knew that about the 20th century, but we've carried out the computations on this somewhat simpler situation with the goodness of fit. Let's go on and look at a test of independence. Our second chi-square test is one that will use two variables. I'm sticking with males and females, but now I'm looking at how many survived and how many died when the Titanic sank. As the little header says, the prevailing norm of chivalry at the beginning part of the 20th century required that men would provide for the safety of women and children before their own. When the Titanic sank, it didn't have enough lifeboats, and so the strength of that norm can be tested with a chi-square test of independence. So our null hypothesis would be that men and women passengers were equally likely to survive, and our alternate hypothesis was that men and women passengers did not survive the Titanic in proportion to their numbers on the passenger list. So I need to compute my expected values if the null hypothesis were true. So that I'm not saying that they would survive in equal numbers, but proportionate to their part of the passenger list. So whatever proportion, 400 out of 1,100, almost 1,200, that's a little more than a third. About a third of the passengers were women. Nope, I am right. About a third of the passengers were women, so then about a third of the survivors would be women, if the null hypothesis were true. So let's compute our expected values and then carry out the rest of our test. So I have here our data, we can see almost immediately that there are quite a few women survivors, many fewer male survivors, and the reverse is true for those who perished in the sinking. So it already looks on the face of it as though we have a situation where the alternate hypothesis will be true. But let's carry out the computations and see what we get for a statistic. So the expected value is a little bit harder to calculate. If you remember, with the goodness of fit, we were just looking at a 50-50 split. The equation from the textbook tells us that we take the row total, whoops, I'm going to need parentheses. We take the row total, we multiply it by the column total, and then we divide that multiplied amount by the grand total. So it gives me an expected number of men who would survive if gender had nothing to do with survival. And notice it does have decimal places in it. There is no requirement that the expected value be a whole number. The observed value will be, because those are actual counts, but this can be a decimal place. I can't do a drag situation. I can't click on this and drag the cell. It would correctly go to the next row, but for the column total it would go into this blank cell, and that wouldn't work. So I'm going to have to type it all 4 times. I open my parentheses, row total times column total, close my parentheses, that's the numerator. I divide by the grand total and put in those values. I do the same thing for the women. The row total times their column total, it's a different column, but I still am dividing by the same grand total, and the final one comes in the row total times the column total divided by the grand total. Now, if these numbers all worked out accurately, they should add up to the same 1188, give or take a little bit because of the decimal places. So just to check that out, I'm going to drag over all of them as a sum, telling Excel to add it all up. And as you can see, even though we've got some decimal places and probably more that are not showing, even though these numbers look quite peculiar, it's telling me that they add up to 1188 people, just as the actual passengers did. So the calculations for this expected value is saying, if my null hypothesis were true, this is how the survival and the people who failed to survive would be distributed according to the number of males and females. So I need to compute my actual chi-square parts, which is where I put on the top the observed minus the expected. I square it and then divide by the expected. And you probably remember that we used this power function, and I'm going to, I'll move the spreadsheet back after we finish doing this. I'm going to take the power observed minus expected squared over just the expected value. I think there's a typo there. So here we go. Equals power. It's my function. The first thing I need is the number, and it's my observed minus my expected. I put in the comma to go on to the second part, tell it what power I'm raising it to. So that's the numerator. I have to divide by the expected value. I hit enter and it goes into the cell. I do the same thing, and this one actually I bet I can do by dragging down. Yep, I bet it'll let me do it, and I bet it will let me drag both of them to the right. And this time it worked because when I went from this cell down, it took this, went from this observed to this observed. It went from this expected to this expected, and all the computations were only with those cells, so it worked fairly well. And I'm going to go over here, even though we won't be seeing this again, and correct. This should be just the expected on the bottom. So I'm going to correct that so we've got the right version of the power. So now I've got the 4 components, and we can tell we're going to get a situation similar to what we had on the first spreadsheet. Just looking at this, I can tell that this is going to add up to 300 or 400 for my chi-square statistic. So I'm saying that I take the sum of these 4 numbers, and that's my actual chi-square statistic. When I'm looking at a test of independence, my degrees of freedom is the number of columns minus 1 times the number of rows minus 1. And it means rows of actual data, the males and female or the survived and died. These totals are marginals that just help us with the computation. But I actually have 2 categories of gender and 2 categories of outcome. So 2 columns, 2 rows. I'm still having only 1 degree of freedom. So I'm going to use my chi-square dist.rt and look at equals chi-square dist.rt, and I need 2 parts for it, the actual statistic and then the degrees of freedom. So there's my statistic. There is my degrees of freedom, and we can bet on seeing another one of those numbers in scientific notation. This time I've got 85 zeros before it. So I'm seeing that the probability of getting this distribution, 128 male survivors out of 700 and 300 female survivors out of just 400. I would not get this distribution except in this extremely minute quantity of times by random chance. So our initial question about the prevailing norm of chivalry is being shown in a very strong way here. The chances of getting this kind of result by random chance is basically impossible. So I will reject the null hypothesis and go on to accept the hypothesis that the norm of chivalry was active when the Titanic sank. So you can see how we've carried out the computation to get the chi-square statistic and then to get the p-value. It's very rare to see a p-value that's this teensy. Both of the hypotheses that we were testing were ones that we knew ahead of time were probably going to be rejected. The ones that you'll find in the homework problems are going to be ones where the chi-square statistic will not be anywhere nearly as dramatic as these are. So I wish you good luck with the homework, and I'm sure it feels much easier to deal with a simple concept related to counts after all the time we've spent with analysis of variance. Good luck.